Okay, I'm going to wait until a minute is passed to start. Hello, I'm Jay Lockman, sitting in for Jim Jackson, who's away, and welcome to the latest in our series of GBT community webinars. Let me give you a little bit of news before turning it over to our speaker. On the screen, you see some of our summer students, REU students, engineering students who are arriving for the summer in Greenbank. You can see that they come from quite a range of institutions and are working on things from engineering to RFI mitigation to science. We welcome them and look forward to an interesting and productive summer with them. On the news, by now, the 23B proposal dispositions should be out, so you should have received them and understand the status of the projects you propose to do. The GBT is in full operation with our suite of receivers, and we're entering the summer maintenance period, but we'll be operating pretty much normally for the coming months, except for an extended shutdown toward the end of the summer. I don't know the specific dates, but those will be to take care of some issues again with the track and with the grout that supports the track. We believe that we've cracked the case that on the problems that have been plaguing us for these past few years, and look forward optimistically to full continued operations once that fix is in. The last bit of news is that, two things. We will have a GBT presence at the AAS, so stop by and see our booth if you're going to be in Albuquerque in the coming weeks. And we will have a new data analyst joining us. Jay Frothingham will be coming to us in a few weeks, and that will make 3 data analysts, and we hope that will reduce the burden on some of our support staff for giving you support for your observations. Let me turn it over now to today's speaker, Pedro Salas from the Greenbank Observatory, and he'll be speaking at Revisiting the Density of Ionized Gas in the Galactic Plane with the GBT. Let me remind everyone that this is being recorded for future viewing, and that if you have questions, please submit them using the Q&A button on the lower part of your screen, and he can field those at the end of the time of his presentation. So take it away, Pedro.
Thank you, Jay. Can you hear me well? Today I wanted to share, thanks for the opportunity to share my work with you. This is a project that we started when I first arrived to Greenbank with Lauren, Mateo, Kim, and later more people have been joining in. But I wanted to focus on the initial spark and show a bit where we're going from this initial spark going forward. And this is a project where we're trying to characterize the properties of the ionized gas in the galactic plane using the GBT, in particular its density. And let's see, okay. So it's a bit of a motivation. We know that ionized gas is one of the major components of the interstellar medium. And we know that this ionized gas is in large part a byproduct of stellar feedback. Here on the right, we see, for example, a simulation of volume of galactic gas under different feedback prescriptions, in particular no feedback, using supernovae only, ionization only, and then combining supernovae and ionization. And we can see that the picture is quite different when we include ionization, right? So we know that this is also one of the major ingredients in setting the properties of the interstellar medium. And as such, we would like to try to understand better how this takes place going the other way around, looking at the products, the ionized gas, characterizing those, and hopefully from there we can jump back and understand different sources of ionization and how ionizing radiation is impacting the interstellar medium and on a broader scale evolution of galaxies. The way we're doing this is using radio recombination lines from hydrogen. And why? Well, the most obvious reason is because work at the GBT, and GBT is a great instrument for observing these lines, but they're also very good probes of ionized gas on their own. The first thing, as we can see here on the left, is that these are extinction-free probes of the ionized gas. On the leftmost panel here, we see H-alpha emission in the optical, which is, I would say the best probe of ionized gas in general. But as we're sitting in the galactic plane, dust obscuration makes it it doesn't allow us to go very far using H-alpha. And that's seen here in the left side of this image. There's a lot of dust between us and the star-forming region, so the H-alpha emission is basically obscured, but we can pick it up very well in this 1.4 gigahertz with the hydrogen 166 alpha emission. Another thing that's quite interesting about these recombination lines is if we observe them at multiple frequencies, we can characterize the gas properties. So that's shown here on the right, where we have some of the frequency bands covered by the GBT, C band at 5 gigahertz, and the two prime focus receiver ones. And the black lines show what we would predict for the line emission under two different sets of gas conditions. In particular, you can notice both models have the same emission measure. So at 5 gigahertz, the emission is pretty much the same. But as we go towards lower frequencies, measuring effects come into play, and then the gas at different densities would have very different emission characteristics. So by tracing the emission as a function of frequency, we can then recover the density of the gas. So that's what we're trying to do with the GBT now. And like I said, this was just a little spark that started in 2019. And the initial observations we did during this time that Mateo carried out very diligently were observations of 3 regions on the galactic plane where there were either no known H2 regions or only radio quiet H2 regions. And we observed this with the 342 megahertz receiver and the 800 megahertz receivers, both prime focus receivers on the GBT. Integration times varied between 2.5 hours and a few minutes, depending on the region and the frequency. And something that was very encouraging was that the noises we could recover are very close to a thermal noise. Again, pointing out how the GBT and Vegas in particular are great instrument for doing this kind of work. Another big motivation for doing this was that around that time, the GBT Diffuse Ionized Gas Survey, GDIGS, work led by Lauren Anderson and his group at West Virginia University, was about to be completed. And this was the first time that we had like this high angular resolution maps of recombination line emission at 5 gigahertz. So we could use this also to anchor and understand better what was happening inside the beam of the GBT at these low frequencies, right? GDIGS has an angular resolution of roughly 2 arc-minutes, and these observations go between something like 16 arc-minutes to 36 arc-minutes. So having GDIGS was very important in order to know what's going on under the beam. In terms of how these regions look like, these are some glimpse three-color composite images of the regions we studied. And here the purple and gray circles show basically the areas we targeted. So there's this one on the left, it's very close to W43. One in the middle, don't remember if there's anything, any well-known H2 region in the field. And in the case of the right, we have M17 down here on the bottom right. And you can see that at least for the two, the left and the center one, there are no known nor candidate H2 regions within the beam. And for the rightmost one, there's a couple of radio quiet regions within the beam. So we're targeting what in the what would be the center and the leftmost panel regions. We will be targeting what we could dub as blank regions on the right, an H2 region per se. But yeah. In terms of the line emission, this is how the what we're detecting at 800 megahertz and how it compares with other gas tracers. So we have in red the 800 megahertz emission, in yellowish the CO emission, and in green the H1 emission, both scaled down to so that they can fit within the display. And this comparison basically is telling us that we're probing gas that's associated with the spiral arms of our galaxy, right? We're not just seeing broad and very extended emission. It's the hydrogen emission. It's basically coincident with where we see peaks in CO. So we know that this gas must be associated somehow with the spiral arms and likely with some of the star-forming regions nearby. In terms of the lines themselves, when we look at them at the different frequencies, what we have here on the top panels are the GDIGS emission in greenish, the 340 megahertz emission in yellowish, and then in gray, the difference between the two frequencies, both extracted from the same apertures of the same size. This, again, why it was very important to have something like GDIGS to do this kind of analysis. And then on the bottom, in light blue, again, GDIGS, and then in red, the 800 megahertz data. In black, the difference between the two. And at the very bottom, what we see is the difference between the 300 and the 800 megahertz data. So in all cases, despite the difference in beam sizes, we see that the difference between the low frequency lines is consistent with noise. And in the case of the differences with respect to a 5 GHz data, it also is very much noise-like, which is, again, kind of surprising given the difference in beam sizes and the potential for probing different volumes of gas. In terms of line properties, they're also roughly consistent with each other in terms of their velocity centroids and line widths. So at least for this analysis, I'm going to make the big assumption that we're probing the same volume of gas in all the lines and that it's filling the beam at the lowest frequencies. So in order to extract physical information from these observed line profiles, what we did was use this model developed by Shaver in 1975, where you have as background a source of background continuum illuminating a slab of ionized gas. In this case, we assume it's homogeneous, though it's very easy to generalize this to multiple volumes or multiple layers along the line of sight, which also, and we also allow for some non-thermal component within the volume of ionized gas. And well, this is basically how the line emission looks like at the end of the, it reaches the telescope. And we use the code of Salgado et al. To compute departure coefficients. In terms of how do we apply this model to our data? Well, what we'll do is take the line emission and then take the predictions from this model, and from that predict, compare that with what we're observing. And the way we're doing this is in the density and emission measure plane. So for each value of the brightness of the lines, or for each value of emission measure and density and temperature, those are our three main free parameters, we can then predict what the line brightness would be and compare that with the observations. And this will give us these curves in this emission measure and density plane. And we have, in this case, four curves for 4 different lines. The GDIGS line at 5 gigahertz, a fiducial line at 1.4 gigahertz, and then the lines at 800 and 300 megahertz. And then the idea is, if we have if the line emission is consistent with a single volume, all these lines will intersect on one point, and then the area covered by the area intersected by these lines is going to tell us what's the range of allowed gas properties. The first thing to note is that just using these lines on their own, we have no constraint on the gas temperature, right? We could vary the gas temperature and we would always find intersections. Each one of these little rectangles shows basically what happens if we vary the electron temperature in steps of 500 Kelvin. Another thing that it's not entirely a free parameter is how much of the background of the continuum we're observing is behind the H2 region. And this is important because this is basically, this continuum is producing some of the stimulation of the lines. So the more continuum we have in the background, the brighter the lines are going to be. And the effect this has on the predictions of the models is displacing these curves to the left if we have less background continuum, or to the right if we have more background continuum, which is a bit counterintuitive, but it's the effect that the stimulation is stronger the lower the density. And then in the rightmost panel just shows what would be the effect if we were to lower the uncertainties in the measured line properties by a factor of 2. This would have the effect of mostly narrowing the range of allowed gas properties along the density axis. So now that we know how this looks like, we can then we also use additional information to constrain the gas properties, in particular the line widths. So if we assume that most of the line widths are set by collisional broadening, we have that in general the observed line widths predict something that's a density that's below 60 particles per cubic centimeter. And we also use the line velocities and to estimate the kinematic distances, and from this try to estimate what fraction of the continuum is behind the volume of ionized gas we're probing, by assuming that the gas is homogeneous along the line of sight. And we also put upper limits to the dispersion measure or the emission measure using the Yao et al. Model for the electron density in our galaxy. And once we have all these ingredients in place, this is what comes out, focusing only on these two regions along galactic longitude of 15 and 31. The middle one, kind of not considering it here because the profile is very clearly a double horn, and the uncertainties are just too large to say anything meaningful about the gas. So what we have here is, first of all, this black line here, that's the constraint from the dispersion measure. This dotted line here, that's the upper limit from the line width. And then in gray, we have the area that would be allowed if we had no knowledge about the background continuum or the temperature of the gas. So it could be quite wide. As soon as we fix what the contribution from the background continuum is, this narrows down, and we do that using the distance. And then we can also use something like the galactic temperature curve to peak temperature, and that narrows things even more to this tiny green slab here around the middle. And we do the same for both regions, and this is what comes out. So in this case, get a density of around 10 particles per cubic centimeter, and in this case, slightly larger. In tabular format, this is how that looks like. And again, the important, or well, what we're mainly after is this density down here. And this is roughly a best case scenario when we do know the background density, the background continuum, and the electron temperature. Once we know this, we can also, well, we also constrain the emission measure and the size of the volume of emitting gas along the line of sight. So in this case, it's anywhere between 15 and 220 parsecs. And in this other case, it's much more constrained because the region is brighter, to something between 1 and 18 parsecs along the line of sight. If we compare this with other works that have tried to estimate the electron density of ionized gas, we see that the results are generally consistent with each other. So for the first region, we arrive something between 3 and 13 particles per cubic centimeter. And though the comparison is not one-to-one because the beam sizes are different and the regions targeted are not exactly the same as those in previous studies, we compare with the work of Paul Goldsmith, where he used the lines from nitrogen. It's the closest pointing to this region gives something 18 plus minus 2 electrons per cubic centimeter, which is close to what we're measuring. The work of Roshi in 2001 gives something like 6.1, so also within what we're measuring. And the previous work, also using hydrogen radio recombination lines by Anantharamaya, gives a value of 2.5 electrons per cubic centimeter. This one is a bit lower than the rest. We studied the differences, and it's mainly because of the choice of beam filling factor. The beams we're using now are somewhat smaller, so the effect is not as big. In the past, the beams were significantly larger, and that correction would tend to give you lower electron densities in general. They also compare the choice of departure coefficients used, and that only accounts for something like 30% difference. So the major effect is really the choice of the beam filling factor. And once we have these values, well, in this case, we only targeted a couple of regions, but we can still do some interesting things just to show something. In this case, if we take this density and we assume that the gas is providing a cylindrical volume and that it fills it, we get that to power the ionization of this gas, we need something between 10 to the 49 or 10 to the 51 line continuum photons per second. And if we compare this to the ionization, the total number of ionizing photons produced by W43 and the H2 regions around it, we see that this is roughly between 0.01% or 1% of the total photon flux. So it's very possible to ionize something like this, just considering the nearby H2 regions. And we're also, I think, well, we're also doing other things. So this was very preliminary. We just had 3 pointed observations at 2 frequencies. We're also moving to doing fully sampled maps. And just to show an example here, I'm showing these maps from the Cygnus X region. On the left, we have again GDIGS at 5 gigahertz on the center, and on the right, we have the prime focus observations with the GBT. So we can start doing this as a function of position as well over most of the galactic plane. In this particular case, the work is being led by Kimberly Emig, but we also have a survey called the GBT Diffuse Ionized Gas Survey at low frequencies, I saw Leonardo was in the audience. Leonardo is also part of this team. And the idea is to map the inner Milky Way at these adding these two frequencies to GDIGS to also derive gas densities over most of the inner galaxy as a function of position and velocity. And as a summary, well, hydrogen radio recombination lines are an extinction-free probe of the ionized gas, and we can extract densities from them. And it just happens that the GBT is a really, really excellent radio combination line survey machine. This is particularly because of, well, it's big and it has a great backend, Vegas, which enables us to observe many of these lines simultaneously and average them together. And what we're finding from this kind of work is that, well, we're finding similar densities to what had been inferred before, but now we can make maps. And in one of these particular regions, we find that the ionization is easily powered by the presence of nearby H2 regions and their massive stars. And I'll end there. Thank you very much.
Thanks very much, Pedro, for your very interesting presentation. Let me remind everyone to submit questions through the Q&A in the lower right. And I'm going to start with a question that I had. Do you have enough sensitivity in your 6-centimeter observations to say anything about structure within the beams at lower frequencies?
Yeah, we do have some. It is hard, but you can see some of it, and there doesn't seem to be much structure as far as I can tell. It seems to be just like this very fluffy kind of emission that's just sitting everywhere around the big H2 regions.
Okay. We have another question. Both the WAM survey H-alpha observations and pulsar dispersion measures imply that the electron density is of order 0.03 per cubic centimeter for the general ISM. Your densities are much larger. How do you reconcile that, given that 2 of your 3 fields are blank?
Yeah, as I understand it, the WAM and the pulsar dispersion measure, the combined use of those is generally when we're looking away from the galactic plane. So I would say that's one of the differences, that here we're really looking into the plane itself, right? Where we expect densities to be higher. And then in terms of how do we explain the difference, well, I haven't thought too much about it, but I would imagine that naturally one expects a gradient intensity as we move from the galactic plane, where we have very active star formation and lots of dense gas, lots of cold gas that's potentially being ionized. And as we move towards the halo, those densities are going to drop, and the star formation activity is also going to drop. So you are potentially only ionizing the more tenuous, lower density material. But this is just me hand waving.
Yeah, but before we go on to the next question, let me follow that up by asking, you do have an idea of the angular extent and now the linear extent. So does that say something about the filling factor of the gas you're detecting?
Yeah. I don't have a number at the top of my head, but yeah, it's a very small filling factor. But this, I mean, yeah, this gas should have a
and we have another
factor.
And we have another question here. The sight lines that you analyzed also have H1 and CO emission components. Is it possible to compare the H1 particle densities, the molecular particle densities, and the ionized gas densities for these emission structures?
Yeah, that would be, yeah, we're really, it would be great if we could do it, because yeah, then it could tell us something about what's being ionized, or what's the relation between all these different gas phases. Where I don't know how well we could and how easy it would be to extract density information from the H1 and the CO. If you know how to do that, please drop me a line or something, because I would be really interested.
Okay, we have another question. Do you have some idea of the influence the ionized gas has on potential star formation conditions in these regions?
Yeah, I find that a very interesting question. I don't know. Honestly, I don't know. Yeah.
It strikes me that for the parameters that you're giving, these H2 regions are not tremendously overpressured compared to what's generally expected. I mean, it may be, well, maybe a factor of a few, but not tremendously overpressured. Let's see. Here's another question. Do you expect to see this gas away from the galactic center, I guess in the outer regions of the galaxy?
Oh, that's a good question. Yeah, I know that I'm sure Lauren could give you an answer to that, but I don't know myself. I think if you go deep enough, you should potentially see something, but I'm not sure if the densities would be the same. I would imagine not, but yeah, I don't know for certain.
Okay, we have one final question. Do you plan to use the FAST radio telescope for these purposes?
So there was a very nice, well, they're already doing a great survey, the Galactic Plane Pulsar Survey, which also includes recombination line emission at 1.4 gigahertz. And they are, yeah, the data is public. The only issue there is that, or not issue, but something that we need to remediate is that they're covering different regions than what we're doing. But for example, for Cygnus X, they're covering Cygnus X, so we could do that, and we would have to extend GDIGS and GDIGS low towards the regions that they're mapping, so we can combine these two telescopes. That would be really, really nice.
Well, that's all the time we have live. I would encourage people, if they have other questions, to contact Pedro directly. Let me thank Pedro once again for his presentation and remind everyone that it was recorded, and so it will be available on the GBO website within a day or two. Please join us 2 weeks from now on June 7th, when we'll have Willem Bond speaking about VLBI tails of 2 megamasers. We look forward to seeing you then. Thanks and goodbye.